This is just a short video on enthalpy or heat at constant pressure of reaction. So now I guess we need a reaction we'll consider, because we're going to consider the reaction giving off heat, and it's a balanced reaction. So we'll say 4 moles of ammonia with 5 moles of oxygen give our products. And it's a balanced reaction, so it's really important to remember when we say enthalpy of reaction, it's for a balanced reaction wherein we may have coefficients, and I want to talk about how we deal with those. So let's say we had some weights for ammonia and O2 and just arbitrary numbers, and we have converted using molar mass those two numbers to moles. And let's say it came to 20 moles of ammonia and 25 moles of O2. Now that's perfect because it's the exact amount that I need to react both of these completely, but just for sake of making an easy video here, let's say we found this to be 20 moles and 25 moles. And we react that, combine those two together, and we get a total amount of heat given off of 1,000 kilojoules, and again just an arbitrary number. How do we find the enthalpy of this reaction? Well, I want to show how we can do that with either the ammonia or the O2 to get the same number, the same amount of heat. So let's take ammonia first. Let's take the total heat and divide it by the total moles. So we're simply going to take 1,000 kilojoules and divide it by 20 moles of ammonia. Now if I do the math, then I'm going to end up with 50 kilojoules up top, and over, in a sense, we can leave the 1 down there, 1 mole of ammonia. It's really 50 kilojoules per mole, but we can just say 50 kilojoules per 1 mole. Now I notice, though, that the reaction doesn't use just 1 mole of ammonia in this balanced reaction. It uses 4 moles. So all I need to do, once I've taken the total heat of a reaction given some amount of these two reagents, picking one of those, if we have that as our limiting reagent and that's all consumed, we would divide the total heat by the total moles, look at the, I guess, coefficient and say, oh, I need to have that down here. So what I'm going to do is times the top by 4, times the bottom by 4, that's equal to 1, and we can say the amount of heat of reaction for this reaction is 200 kilojoules per 4 moles of NH3. Now just to show how we can get the same number using oxygen, let's start with oxygen and we say still the total heat over the total moles of O2 that reacts, 25 moles of O2. If we do that math, we're going to get 40 kilojoules per 1 mole of O2. That's what we're really saying, keeping this unit here, 40 kilojoules per mole of O2. You may just see it as this. But again, we don't have just 1 mole of O2 that's consumed. We have 5. So what do? Times the top by 5, the bottom by 5. That's going to give us exactly what we had as the heat of reaction, but now we're saying per 5 moles of O2. This is important because sometimes it's hard to remember that the enthalpy of reaction, the amount of heat, can be written in terms of per moles of reagents that are different, or we can even have written this as 200 kilojoules per 4 moles of NO that's formed. One last thing. Don't forget that if you are given as a starting point some amount in grams of ammonia and you convert that to moles and you want to know how much heat is given off from the reaction, you'll have to take that much in grams, or sorry, in moles, times it by this conversion, making sure to have the 4 in this conversion, not just multiplying it by 200. So if you have, again, some new amounts of these two and you wanted to know how much heat was given off, you would convert it to moles, times it by this conversion, but make sure that 4 is in there if they gave you ammonia. If they gave you oxygen, you'd use this conversion. And again, you would make sure to find the amount of moles of oxygen that was used to give whatever amount of heat, and you would then times it by this conversion, 200, but making sure to divide by 5. That's it. Bye-bye.